Hello everyone, welcome back to my channel, Predicting the Future. Today we're gonna talk about a little bit larger topic, which is probability convergence. I'm gonna go through the sections what I'm gonna talk about today, so you can jump over the sections you are interested in and skip those that you already know. Today we're gonna talk about a couple of convergence. The first one is convergence in probability. Which is a, which is a stronger convergence compared to another convergence we're going to talk about, which is weak convergence or converge in distribution. And we're going to talk about the relationship of convergence in probability and convergence in distribution and convergence almost surely. And But the weak convergence is a little bit larger section. We're going to talk about a couple of important lemmas and theorems. The first one we want to talk about is the Pomental lemmas, and then we're going to talk about the Slatsky theorem. We'll then talk about one second. Let me make this a little bit smaller, and then we're going to talk about tightness. Or bounded in probability of a sequence of distributions, and the Hadley selection theorem, which is very important one, and then we're going to talk about the central limit theorem and prove that central limit theorem. So that's our agenda today. So let's begin. So convergence in probability, as you see the definition, xn converges to x in probability if the probability of absolute value xn minus x is greater than any epsilon goes to 0 as n goes to infinity. And that's noted as xn arrow with a p on top to x. A couple of properties. So if p is a number greater than 0 and if the expected value of xn to the power p goes to 0, then xn goes to 0 in probability, and that is easily provable using the Chebyshev inequality. The second one is also easy to prove, which says that if xn converges to x in probability and yn converges to y in probability, then the sum of xn plus yn converge to x plus y in probability. And then the next theorem is it's a very useful theorem that if we want to prove something converge in probability, we can prove that if the sum xn converge to x in probability is equivalent to given any subsequence of xn, there's a further subsequence of that subsequence converge to x almost surely. So if we can prove that this two is actually equal, then we can prove one or another. So let's prove that. Why? So as you can see, this is very similar to the mathematical analysis in real numbers or complete spaces, complete compact spaces. So let's prove that. So the first one, if xn converges to x in probability, and then we want to prove that there's a further subsequence that converges to x almost surely. So let's given any subsequence xn converges to x in probability, and then because it converges in probability, then for each k there's a further xn mk, which is correspond to each k, such that this xn mk minus x greater than over k is less than or equal to 2 to the power minus k. And then we find that for each k, so we know that the sequence for the k of this one is all less than or equal to 2 to the power minus k. then the summation will be finite. This is because summation of 2 to the power minus k is a convergent sequence. So we know this is a convergent sequence, and by the Borel-Cantalian lemma, we know that the probability of xn mk minus x, absolute value of that is greater than 1 over k, infinitely often has probability 0. And therefore, xn mk converges to x almost surely. Now let's prove the other direction. If we have if xn converges to so if every subsequence there's a further subsequence converges to x almost surely, then xn converges to x. So that direction, since every subsequence is there's a further subsequence that converges to 0, those are just numbers, right? So that's numbers in a complete real line, on the real line. Then by the completeness of R, we have that this sequence, this number sequence converges to 0. So that's the proof of this theorem.